And to get started with that, let me draw a ring here. If you understand what moment of inertia is, you could probably come up with the moment of inertia of a ring without doing any math at all. And that requires just the definition. If you don't remember what the definition of moment of inertia is, then I can't help you, but the moment of inertia is a measure of how the mass is distributed about the axis of rotation. That's what the moment of inertia is. It was a summation that took each piece of mass and multiplied by how far away from the axis of rotation it was. Well, if we're doing a ring about its center and we're spinning the ring this way, isn't it pretty clear that every piece of mass is the same distance away from the axis of rotation? Because it's a ring. So the math we're about to do is largely redundant. I'm doing the math because I want you to know the process. But every single piece of mass of this object is the same distance r away from the axis of rotation, which is why the moment of inertia of a ring is just mr squared, because every piece is the same distance away from the axis of rotation. But we're going to do the math for it, which is, again, redundant. I don't think it's necessary if you could reason it out. But if you can do the math for the ring, you'll understand the math for a disk, which is not true, right? The disk has mass spread out throughout the whole thing. So that's why we're doing the ring, not because I think it's a super valuable exercise, but because it builds one more step. And the reason why the ring is a useful tool here has to do with some of the knowledge that you guys don't have about coordinate systems and how they behave. So that's one of the reasons we're going to do the ring. Now, we're going to do the ring using an axis of rotation that is perpendicular to the plane of the ring. I'm going to define a few things that I think are obvious. For example, I'm going to say that the ring has an entire mass of m and a radius of capital R. All good? All right. Determine how to express the mass density of the object. Kind of already said it, but I'm going to do it again. The mass density of our object is m over 2 pi r. This will be the mass density of the object, the mass per unit length. So I'm taking the circumference of the object, that's how long it is, and I'm taking the mass of the object, and I'm expressing its density. Later on in this problem, we're going to use this ratio to figure out how much a piece of the object's mass weighs, or is. All right, so we want to express a location of each piece of the object. So for this next thing, you need to choose a small part of the entire ring. So I am choosing this spot right here, which is a bit of arc length. But I'm going to label it dm because it is a piece of the entire mass. Eventually, my goal is to come up with a ratio of how much the mass of that object is related to its length. And that's eventually where I want to get to. So I can solve for dm and have something to substitute into our integrand. But I need to come up with a way of pointing to each piece, a way that will define the first piece and the last piece for us. And I can think of two different ways to point to the edge of that piece. One way, and I'm not doing this accidentally, I'm trying to teach you something about coordinates. So I'm going to put an XY coordinate system over the top of this. And I think you guys would agree that I could point to where this piece is by going over a distance x and up a distance y. Right? That would allow me to point to each piece, correct? Now, I don't know if this is the most efficient way to do this, but it would be effective. The problem is that for every x, there's a relationship between x and y. It's not just every x goes from 0 to the edge and every y goes from 0 to the edge. For every x, there is a specific y, right? Because you guys know the equation of a circle, correct? So you understand that the equation of a circle is x squared plus y squared equals r squared. So x and y are related. If I was trying to find the limits of where x begins and where x ends, although I know there's going to be an x at 0 and an x at r, each x and y are paired together. That makes for a complicated arrangement because I would have to figure out how to express where every piece is using x squared plus y squared equals r squared. I'm not sure that's the easiest way to do so, but there are other ways to point to the edge of this object. The other way, and you should know this, I don't know if you do or not, is to go out a distance r and then over an angle theta. Does that sound familiar to you? Because you guys have learned two different coordinate systems. You've learned polar and you've learned Cartesian or rectangular. Now, this isn't a trick, but when you're trying to figure out why we have these two different coordinate systems, it's because sometimes it's easier to explain where stuff is or the shape of an object using one coordinate system versus another. You get to choose the coordinate system that best matches what you're trying to show. So if I'm trying to deal with something that is squared off or rectangular, I would probably use rectangular coordinates. But if I'm trying to define something that's round, I'm probably going to use polar coordinates. You guys understand that there's like 5 different coordinate systems out there, right? How many of you are aware of all 5 coordinate systems? There's rectangular, x and y. There's Cartesian, x, y, and z. There's polar, r and theta. There's cylindrical, which is r, theta, z. It describes things by using a cylinder to figure out where every piece of the object is or where every point in space is. And then there's spherical, which is rho, theta, and phi, using 2 angles and a length. So there are lots of different ways of identifying a place in space. You use a coordinate system that matches the geometry you're working with. So if you're talking about the solar system, you probably use something like polar coordinates because the solar system is largely flat, but is projected at a circular path. If you're talking about the shape of a star, you'd probably use spherical coordinate systems because it's going to be a sphere. Do you understand where I'm going with this? All right. So if I want to define where every piece of mass is, I think it would be far less complicated to use polar than use rectangular. Because I think rectangular will be hard to define where every piece of mass is. With polar, I think we can all say that the first mass starts at 0 and the last mass is at 2 pi. I think it's very easy to define where every piece of mass is. But with the x and y, I think that would be hard. All good so far? All right. We'll see. We need to use our location variables to describe the size of dm. Now this part tends to be tough, but I'm looking at what appears to be a small piece of arc length that I'll say is ds. S is a traditional letter used for arc length. And this from here to here is our arc length. But I don't want to use ds, I want to use r and theta. So if I wanted to describe how big ds is, it seems to me I would go out to the first part of my piece of mass and then just go over a small increase in theta. Does that make sense? Imagine that you were using a compass. A compass has a fixed value for r. If you were making an arc, you would just scratch out a little bit of theta to get a piece of the arc. Does that make sense to you guys so far? And I'm going to base this on something you were already supposed to know, that delta x is equal to delta theta times r. Do you remember that from earlier in kinematics? It's the same thing here. We're just going to say that ds is equal to d theta times r. This is a small piece of arc that is made by going out a distance r and then over a small displacement in angle d theta. Now, I'm being super careful and super slow and super diplomatic, with the hope being that you're writing things down about why I'm making the choices I'm making and where r d theta came from. I didn't invent it. Put it in your notes so you know where these things come from. So when you're studying it, you don't have to come back to me and say, Mr. Sheldon, where did r d theta come from? I'm telling you where it comes from. I'm saying go out a distance r, and then to find out how big your arc length is, sweep out a small displacement of angle. All right, got it down? Well, with that, oops, didn't want to do that. I want to do this. With that, I think we can begin to build our integrand. I'm going to use this first, and I'm going to say m over 2 pi r is equal to dm over d theta times r. I'm replacing ds with something that's using our pointer variables. That's what we said. We want to come up with a way of expressing the density of the object compared to the density of a piece, but I have to define that piece by pointer variables that we created for this particular example. So we created r and theta to point to each piece. And so now I can solve this for dm, noticing that r's cancel out here, and I'll get m over 2 pi d theta. So we've come up with an expression for dm that we can substitute into our integrand. So now we pull up our formula for calculating moment of inertia. And we have to populate it with the variables we're going to use for our integration. So just a reminder, dm stands for exactly what we just described, a piece of the mass of the whole object. We have to integrate over the entire object's mass. But the r squared here stands for where that piece is relative to the axis of rotation. It is the distance from the axis of rotation to the piece of the object we're looking at. For every one of these, you have to evaluate what r is going to be. For this one, it's super easy because every piece is the same distance away. So I'm substituting in the pointer variable that we already know exists, the radius of the object. But dm, we're going to substitute in all the things we have that replace dm with information about our pointer variable. And now we're going to assess and write out where's the first piece and where's the last piece. Right, we are populating our integrand with something that we can actually integrate now. Now that's done, your job is just to integrate this. And you guys have the skill set for that because we've learned it already. So I'm going to start by finding out which pieces of this summation are the same for every summation, meaning which of these letters are constant over the entire ring. For example, can you name one that's constant over the entire ring? R squared is, sure. What else? The mass is, what else? 2 pi, that would be true. So all of those are constants. We can take all of them outside of the summation because they're going to be the same for every term in our summation, which just leaves d theta. So now you have to integrate d theta. That shouldn't be tough, but I don't see a theta in there anywheres. So you guys are supposed to remember that if you don't see a variable or a number there, that there's an implied number. What's the implied number? 1, which we're going to say is theta to the 0 power. Again, we've done this before. I'm expecting you to remember things. So now I'll use my antiderivative for a polynomial. And that means adding 1 to my exponent and dividing by the new exponent. So I've done the antiderivative, but this is an integral, so I have to apply my limits. So I put in my top limit first, and then subtract when putting in my bottom limit. And then I know this is super obvious, but 2 pi cancels and we get mr squared. And from the very beginning, we knew what the answer was going to be. But the point is to go through a process that shows that it does produce the obvious answer. Every piece of mass is the same distance away from the axis of rotation. We get mr squared. Part of doing this particular problem is to help you see the process and to hopefully build up a little confidence that this process will work, even if you don't fully understand it. So this process works. It produced exactly what we expected, that the moment of inertia of a ring is just that of any object a distance away from the axis of rotation. It's just that every piece of mass is the same distance away. Now let's get to the one that I really want to do today. There's multiple ways to do a disk. Your book does it one way, and I would encourage you to look at the way the book does it. Not because it's better or worse, but in some ways, the book's method is simpler. Because what the book's going to do is it's going to use what we just figured out, the moment of inertia of a ring, and it's going to sum a bunch of rings together. So it starts with a ring, believing the ring is okay, and does a bunch of concentric rings, and proves 1/2 mr squared from the group of rings. We, on the other hand, aren't going to do it that way because I want to show you something else. And I think this has value. So we're going to follow our process, same procedure as before, and we're going to start by identifying things about our object. For example, I'm going to define that the disk has a mass m and a radius r. Defining our disk. This object isn't linear. This looks like a surface. So if I want to describe its density, I think the best way to describe its density is m over pi r squared. Take the entire mass and divide by the entire area of a disk. Because I think I'm going to be breaking this up not into individual lengths, but into individual pieces of area. Does that make sense? Remember, you have to break it all up and point to every single piece of mass. So this doesn't look like it's got linear symmetry, but it does look like it has some kind of surface symmetry. My next job is to identify a piece of the object to use symbolically as a means of describing the whole object. So I'm going to draw not a length this time. I'm going to draw a square. And I'm going to say this square is my piece of mass dm. But it's actually a piece of area. In fact, I'm going to say that the area of this piece is dA, a piece of the area. It's not a length this time. It's an area. Now I have to find a way to point at this piece, and I need to find a way that I could use it to point to every piece of this object. So I'm going to again put down some point of reference. Since I'm going to use polar coordinates, I just need one line here to act as 0. And I'm going to point to this object in a way I hope you find to be obvious, but maybe not. I'm going to start by going out a distance r, then over a distance theta. So I'm going to point to this object by saying it is a distance away from the center, I'm going to use the obvious thing here, r for a radial, and that I am an angle theta away. And I'm pointing to one corner of this object. Can I point to every corner of every piece of the object using r and theta? Is it clear that there's a row of boxes along this line, starting at 0 and ending at capital R? And then I go over a little bit and there's a row of boxes here. Do you guys see what I'm saying? So under that guise, I think we can agree that theta is going to go from 0 to 2 pi, right? And then along each one of the thetas, there's going to be an r that starts at the center and goes to the edge. Will this define every box that we could possibly draw on this object? I think so. All right. So our next job is to define the size of our object. But before, we were defining a length. So you'll remember we had one of the lengths was just going out a little farther in the x direction. So we had dx for the bar. And our next length was a piece of arc length. So we went out a distance r and went a little bit more in the direction of theta to carve out a small arc length. But this is a area. This box has area, and we have to define the area by using something we already know, something like length times width. When I look at this shape, I can say that this could be the width of the shape, and this could be the length of the shape, or vice versa. I can't use L and W for length and width. I have to come up with something that is in terms of R and theta. So I think width will be easy. Because if I think of width, I went out a distance R. I think I'm just going to go a little bit more along R, making my width dr long. Right, delta R, a little more in the R direction. And my length, well, my length is going to be, I think, pretty easy. I think this is an arc length. You guys see why I think it's an arc length? I mean, I know I drew it like a square, but the truth is it's like a little piece. So I'm going to assume that this is going to be r d theta, just like before. Stay at the distance r, but sweep out a small angle d theta. Because I don't know if it's clear, but what I'm really drawing is something like this, where this piece is like a section of this pie. And I'm defining its area as length times width. Now, this class is pretty smart. It probably has occurred to you that this length and this length aren't the same. But in calculus, the difference between those two is so infinitesimally small that we don't have to worry about it. I mean, if you want to consider how small it is, remember, dr is an infinitesimally small piece of length. D theta is an infinitesimally small piece of area. The length of this side would be r d theta, it would be r plus dr times d theta. That's how big that side would be. So if I was using that side, this side, instead of this side, that would be the length. And consider, you would still get r d theta, but then you would also get this dr times d theta, something super, super small multiplied by something super, super small. So that's super small squared. So extra jumbo small. Again, I know it sounds ridiculous, but the idea of calculus is about these things being so small they don't factor into your answer. And I can prove it to you. So instead of taking you through an entire year of calculus, I want to kind of prove why this works. And to prove it, I'm going to do an aside. I want to show you something that's not about moment of inertia, but should help prove why this works. I'm going to take you on this trip, but not all of you are going to understand this trip, but it's okay. Those of you who do, I think, will appreciate this. I have a piece of area. If I integrate over the entire area, I should get the area of the piece. Does that make, I know that sounds like a lot of double talk, but my piece of area ends up adding up to be a circle, of which we know the area of a circle, right? Known it since third grade, pi r squared. So it seems to me if I substitute in the length, dr, times the width, r d theta, if I integrate this over every single piece, I should get pi r squared. Let's see if we do. Unfortunately for you guys, this involves you understanding something here. I'm adding up two different sets of variables, right? I'm adding up the variable r, and I'm adding up the variable theta. Because I'm adding up two different variables, I need to do two different sums, one for r and one for theta. Whenever you are summing an area, it's always two dimensions. It requires two sums. If you're summing in 3 dimensions, you can probably imagine there'd be 3 of those. Now, lucky for us, we go from 0 to the edge of the disk for every single theta. Do you guys follow that, what I just said? Meaning, we start at the inside and we go to the outside for this theta. And we go start at the inside and go to the outside for this theta. So we are going from 0 to r for every single theta. Does that make sense? I'm saying this because this works for a circle because r and theta are disconnected, right? For every theta, we have the same range of r. Now, there are shapes where that's not true. A pinwheel, right? That's not true, right? For every theta, we have a different range of r. Do you guys see that? We start from the center. Sometimes we'll go all the way to the edge. Sometimes we won't. This is where r and theta are connected. You would need an expression between r and theta because we don't go from 0 to the edge for every single theta. But because we go from 0 to the edge for every single theta in a disk, I can break this up. I could do one summation that has to do with dr, and I can do a completely separate summation that has to do with d theta. If they were connected, I would have to do them in order. So there's a process if they're connected. You'll get that in Calculus 3. Now, before I do this, I do have to collect terms, meaning anything that r has to go with r, and anything with theta would have to go with theta. There's nothing to go with theta, but I did have an r. So I moved my r over to where it goes. R is going to go from 0 to the edge, and theta is going to go from 0 to 2 pi. We do these separately, so I'm going to do the r first. This is r to the 1 power, so my antiderivative will be r squared over 2 from 0 to r. I see no theta, do you? So that means theta to the 0 power, so my antiderivative will be theta to the 1 power, evaluated from 0 to 2 pi. Still good? Well, this is area. So r squared over 2 times 2 pi, right? 2's cancel, and we are not surprised by this. We have known for most of your lives now what the area of a circle is. But how do you think they found the area of a circle? And if you want to prove the area of a circle, we've just done it. Now, this is not how the area of a circle was found. The Greeks did this long before there was calculus. But what I'm trying to tell you is that calculus should support math, and it clearly does. So by doing this process, a little bit of confidence, and that we're okay not worrying about the dr times d theta, that's just a tiny, tiny little bit, and we can throw that away. So now we go back to work. meaning m over pi r squared is our density. We have to set that equal to dm over dA and solve this for dm. Now, we're going to sub in the variables we're using, which in this case happen to be dr times r d theta. Those are the variables we're using for dA. And now I'm going to cross multiply to get dm by itself. M over pi r squared r dr d theta. I know, I've said it out loud a lot, r dr. Yeah. Now we bring up our expression for moment of inertia. And we try to build our integrand. Now, we have a couple r's here. Let's make sure we know what each r means. This capital R is just the radius of the disk. That's a constant. I'm not worried about it. But this lowercase r here. So r represents the distance from the pivot point to where each piece of mass is, and that's true here and here. So these are the same values. So I don't have to worry about doing any replacement. They represent the same thing. So now it's just substitution. So I equals the integral of r squared times dm, which is m over pi r squared r dr d theta. All right, there's two integrating variables, so I will add my second integration there. I will drop down a line to deal with anything that's a constant. I think there's a bunch of constants. I think they're all right there. So I'm just going to pull all those out. I'm going to go ahead and collect the terms that are the same. So I'll have the integral of r cubed dr, and I'll have the integral of d theta. I've collected all the variables. And I'll put in my limits. R is going to go from 0 to r, and theta is going to go from 0 to 2 pi. All right, this is just math now. All right, I'm going to do the same thing I've been doing this whole time. M over pi r squared is just a constant. R cubed, add 1 to the exponent, divide by the new exponent. 1/4 r to the 4th, evaluated from 0 to r. Go to the next one. Well, that's just going to be theta, evaluated from 0 to 2 pi. All right, sub in. So it looks like this will be 1/4 r to the 4th times 2 pi. There's not a lot to do next. You see the pi's cancel, right? And I have 2 times 1/4, which will be 1/2. And I have r squared and r to the 4th. Do you guys see all of those? So this clearly reduces to 1/2 m r squared.